Now in last video, we had delved into integral world of filaments, the molecule which is containing 60 carbon atoms or is made of 60 carbon atoms, and how such a molecule might serve as a cage to trap certain atoms or molecules like organic compounds and deliver it to our planet from outer space. Now let us see some of the other elements and whether such elements have come from the outer space. The current video is about geologic and cosmic abundance of rare earth elements, which is widely used in today's many technological applications. So without wasting much time, let's dive into it. Geologic and cosmic abundance of rare earth elements. The periodic table of elements is grouped into S, P, D and F block, wherein rare earth elements from lanthanum to lutetium, they come under F block elements. Lanthanide contraction is what is observed from atomic number 57 to atomic number 71. And it is a phenomenon that is a result of poor shielding of 4f orbitals. This poor shielding is due to decrease in size of the atom or ion due to increasing atomic number and effective nuclear charge. Most of the rare earth elements, they show anomalous behavior with mainly 3 elements under D block, typically scandium, yttrium and titanium. With scandium and yttrium considered to be as rare earth elements due to their similar chemical properties. However, they are different from rare earth elements in terms of their electrical and magnetic properties. Titanium, not a rare earth element, often coexists with rare earth elements in minerals and forms separate oxide phases due to its preference for higher oxidation states and different geochemical behavior. The anomalous behavior of rare earth elements with yttrium stems from their similar ionic radii and chemical properties, allowing yttrium to closely mimic heavy rare earth elements like dysprosium and holmium. Despite not being a lanthanide, yttrium is often grouped with rare earth elements due to its frequent occurrence and shared applications in technologies like phosphors and superconductors. Due to similar chemical properties, it is often difficult to separate rare earth elements from other elements, and therefore technologies like MRT and SuperLead are used to achieve selective separation and recovery of individual rare earth elements. The rare earth elements are grouped into 3 major groups: light, middle and heavy rare earth. Light rare earth elements are from atomic number 57 to atomic number 63, also called as cerium group. Heavy rare earth elements are from atomic number 64 to atomic number 71, also called as yttrium group. Middle rare earth elements are typically from atomic number 62 to 64. Moving on, alongside other elements, specifically titanium, scandium, and yttrium, rare earth elements are found distantly as oxides in mineral ores. Depending on its concentration, accordingly the mineral ores are categorized. So we have minerals with low REE content, minerals with minor REE content, and minerals with major and most probably essential REE content. The concentration of REEs is determined using thermodynamics and thermodynamic data that is collected from experimentations and theoretical models of these mineral ores. The distribution pattern typically of lighter, heavier or middle rare earth elements that is observed in several mineral ores is determined through distribution coefficient of that respective rare earth element in minerals. Although the values of these distribution patterns are not fixed, several minerals tend to range in the values of 0.1 to 1, at least when taken arbitrarily. So let's say if one mineral ore is having a distribution coefficient value of 0.05. 0.05, it is less than 0.1. So that would mean that that particular mineral ore is having very low REE content. On the other hand, if suppose another mineral ore is having a distribution coefficient value of say 1.5 or 1.8. Now 1.5 and 1.8 both are greater than 1. So what would that mean? That this particular mineral ore is perhaps having REE content in major concentration, and probably that REE content would be essential too. So there are several examples that are illustrated in literature regarding the rare earth element content in a specific mineral ore based on their distribution coefficient value and in turn their distribution patterns. Some of the examples are calcic clinopyroxenes, feldspars, mica, olivine, pegmatites, and so on. Whether the rare earth elements have come from outer space is also something that is examined based on thermodynamic studies of the meteorites. It is one of the renowned theory while studying the cosmic abundance of rare earth elements, and that is the condensation theory. This theory talks about using theoretical models that can explain the condensation of elements from the solar nebulae by assuming that a gaseous matter made of some elements, when made to react at higher temperatures, can significantly cause vaporization of those elements, leading to the formation of grains in a thermodynamic equilibrium as the gas would eventually cool. Just like seen previously, the amount of rare earth elements condensed at a given temperature can be calculated by measuring thermodynamic activity of that element in some reference state, usually oxides. Some other thermodynamic functions, like activity coefficient and oxygen fugacity, is also taken into account while analyzing the amount of rare earth element in meteoroids. Because the activity coefficient of rare earth element kind of remains unknown, therefore an arbitrary value of unity is taken into consideration for all the ideal solid solutions containing certain fractions of condensed rare earth element. This condensation theory is bifurcated into many small theories based on the aspect under study. Here we focus on only two out of the many given in literature. So far we have discussed about the condensation of rare earth elements from a gaseous matter made of solar composition, wherein we understood that the amount of rare earth element condensed at a given temperature is calculated considering thermodynamic activity of that element in some reference state, usually oxides. There are other environments also where we can study the rare earth element content. This environment is a non-solar environment. Here, the volatility of rare earth element is determined considering oxygen fugacity of the matter under study. Why oxygen fugacity? Because several astrophysical environments with different oxygen fugacities may have been important in creating grains that were present in our solar system. Therefore, oxygen fugacity can help us determine the rare earth element content as long as the rare earth element is present in its corresponding oxide form. It is very evident to note that the condensation of rare earth element is most probably the relative volatility of several of the rare earth elements as a function of the oxygen fugacity of the gas. Example,
Cerium is found to be present in significant amounts in form of gaseous CO2. It can actually become more volatile if the oxygen fugacity is increased. If we take an example of um, a rare earth element found in a meteorite, we have Chesigny meteorite. This is composed of iron-rich 92 volume percent Fa31 olivine. Now, this iron-rich 92 volume percent Fa31, it basically refers to a material or mineral composition that is predominantly iron, making up to 92% of its volume, with the term Fa31 indicating a specific composition in terms of ferrite content. Ferrite is Fe2SiO4, and it is an iron-rich end member of the olivine mineral series. Fa31 means the olivine contains 31% ferrite and 69% forsterite, that is Mg2SiO4, reflecting its intermediate composition between iron and magnesium in members.
So I hope you enjoyed the video, and to keep yourself updated, do like, share and subscribe to my channel. The second part of this video will be coming up really soon, so I hope you don't miss it.